so that is a lot of problem solving, right? With the Suvat equations, with the kinematics equations. And you probably learned with 1 dimension and 2 dimension now already. And you realize that when you do kinematics in 2 dimensions, it's basically just 1 dimension. There's only one new concept and the concept is telling you to split the 2 directions, the X and Y direction, and treat them almost independently, except for time is being shared. That's the only new concept, right? So 2D is basically 1D just doubled. Right, so nothing too new over there. And to wrap up the whole part of kinematics, the only last thing to do is to show you the formal approach, which is part of the course, right? Part of the syllabus, part of the curriculum. So we need to know that. And also, it also is more powerful in some sense, is because it can deal with non-constant accelerations. Remember, Suvat equations are awesome, but the big limitation is it only works those equations only work if acceleration is constant. All right. So throughout this course, we'll see once or twice where the acceleration is not necessarily constant. So let's write that down. The benefit of this is to deal with potentially time varying. There's 2 main benefits: time varying forces. Right. So if I apply a force that changes with time, then the acceleration will also change with time. The formal approach is the only way to do that. And it's easier generally when we're dealing with multiple objects. Okay, when you're dealing with kinematics of multiple objects, for example, if I drop an apple, right, and first, and then I drop a second apple, I delay it with, let's say, 1.5 seconds, and I drop it again. Then what is the time difference? Do they hit the ground? It will, as you'll see, maybe in your discussion sessions, you'll see some examples of solving that with this approach would be slightly easier, right? So these are the benefits. And to do that, you will need a little bit of calculus. And usually this is where people get scared. And what I'm going to do, I'll basically teach the formal approach in 2 videos. The first one, I'll basically tell you all you need to know about calculus, and it's just really the bare minimum, and you can learn that in 5 minutes or however long the timestamp of this video is going to say. We'll see how this goes. All right. And the next video will apply this into the physics, into the kinematics, and see how this is applied. Okay. Are you ready? All right. So what we're going to do is we're going to do the math part, and I'm going to call that calculus, or I'll call that practical calculus, in 5 minutes, or roughly. Or AKA whatever the timestamp says. Okay, so first of all, this is all just pure mathematics, all right? No physics, just so we understand the math first, and then the physics will become very easy. All right, well, calculus, there's 2 parts of it. There's differentiation, if I can spell it, and integration. Okay, and roughly, right, calculus is basically the mathematics of change. When something changes, okay? Now, it's hard to see how the practical side connects to the concept, so I will sort of disentangle them, right? So we talked a little bit about the concept of finding a varying slope, right? Finding the instantaneous velocity at a point already. And that is really the essence of it, but it's hard to see how it connects to the practical. And that is really the most difficult part about calculus. So we will skip that part. So you basically, believe it or not, you've understood the concept already. And now in the next 5 minutes, you'll understand the machinery, the mechanics of it as well. The really hard part is really just connecting the concept with the mechanics, all right? So don't worry, we'll not spend too much time on it. We'll go with a practical approach. And if we have time in the future, we will cover that as well. So we'll see how this goes. The key thing to know over here is differentiation basically finds the slope at a point. Okay, so as you know, we realize that the velocity, instantaneous velocity, is basically the slope of the position time graph. Acceleration is the slope, acceleration at a certain time, right? Acceleration of an object at a given time is the slope of the velocity time graph. right? So there's the xt graph, there's the vt graph. The slope of that gives you velocity. The slope of a vt graph gives you acceleration, all right? So that's the reason why we need differentiation. And integration is sort of the opposite. It's the opposite of differentiation, okay? So we'll see what that means. And the mathematical use of it is it finds the area under a curve. Okay, so if I have a straight line like this, the area underneath is just a rectangle. It's easy. If I have a straight line like this, the area underneath, let's say XY axis, right? So it's a parallelogram, you can still do it. But if it's a curvy line like this, right, the area underneath, not so easy. And that's what integration does. But in some sense, it's the opposite. It's the reverse of differentiation. All right, are you ready? So let's go. All right. So basic functions first. This is a function, right? So I can write something like 2x plus 3. What a function mean in mathematics is basically if you put an input in there, it will spit out an output. So this is the input, and fx, which equals to this, is the output. Okay, so x itself, the one inside, right? The x is an input, and the whole thing, 2x plus 3, the whole thing is the output. So a function in math is basically a machine that takes input and generates output. Okay, so this is a simple function. I can have another function. You write it like this, right? And this function, we give it a name, right? It goes by the name of f. And this is a function that goes by the name of g. It can be more complicated. It can be like this, right? So what this function tells you to do is take the input, multiply by 2, and add 3. Okay, so f of 1 is going to be take the input, multiply by 2, add 3, so the output is 5. So the input is 1, the output is f of 1, which is 5, like that. This is g is a more fancy function. It has a square, but excuse me, that's fine. Because you take the input, you square it, you add the input again, subtract 1. That's what the function does. Okay. So of course, these things you can plot it on a graph of let's say xy like this, and here that would be some sort of straight line. This would be some sort of parabola like that. That's okay. But now let's say you want to find the slope of this would be f, this would be g, right? You want to find the slope of these things, all right? So the rule is this, all right? Very simple. The rule is if you have x to the power of n, once you differentiated it, you'll want to bring down the n, copy it, and subtract that by 1, okay? That is the thing you want to put in a box. This is not the official notation, but it's easy to remember, okay? The official notation is this. You want to write dxn dx, okay? This is one way to write it, or you can write d dx of xn. So this tells you to differentiate this with respect to x. So you read this symbol as differentiate xn with respect to x, okay? So this reads differentiating xn with respect to x. This kind of reads differentiate with respect to x, xn. So grammatically, both make sense. Mathematically, both make sense as well. You can write it in both ways, okay? So if I have x squared, what you need to do is, I'll use the unofficial notation because it's easier to read. Differentiating that, what you want to do is drag down the 2 and subtract that by 1. Well, x to the power of 1 is just x, right? But just for completeness, to see the pattern, right? So what's x3 differentiated? So differentiating x3 with respect to x is 3, you drag down the 3, x squared, okay? Let's keep going. What's x4? Can you tell me? Right, so x4, you differentiate it, so it's 4x3. Okay, that's calculus. You're done, right? So what's differentiation? What's the derivative? The result is called derivative. What's the derivative of x to the power of 100? It's 100 x99. That's it. Of course, that's not the professional way of writing it, right? So the professional way of writing it is either d dx of x squared, right, is equals to 2x, or you can write it as dx squared dx. So you can almost multiply this here. It's not really a multiply, it's you're differentiating it, but you can write it like this. It's 2x. That's also okay, right? So for example, what we mean over here is d dx of x100 is equals to 100 x99. Okay, now two rules over here is if I'm differentiating something plus something, let's call it a and b or f and g, like this, is equals to, so x squared itself could be a function, right? If I differentiate, let's not confuse ourselves with f and g. Let's call it u and v, right? So if you differentiate two things, it's the same as du dx plus, let's write it this way, plus d dx of v. Okay, so you can, if you're adding things, you can differentiate them separately. And so this is rule number one. The second rule is if you differentiate something with a constant in front, so k times u, if this is just a number or a constant, you can actually pull that out first and then just do the derivative differentiation of u. Okay, so you may want to put this in a box as well. These are the two main rules of differentiation. So what that means is, let's see what this means. So it means if I want to d dx of a function of x squared plus x3, then I just need to differentiate them separately one by one. So that would be 2x plus 3x squared. Okay, so just differentiate this plus them. So you can just do them one by one. That's what it means. If it has a constant in front, so if I want to differentiate 5 times x7, all you have to do is first pull the 5 out and then differentiate whatever x7 is. Well, what's x7? Its derivative is 7x to the power of 6, right? And then you can just multiply it out. So that's 35x6. Okay. All right. So believe it or not, you've learned calculus. So let's see. Let's try to differentiate these two and see if you get it, right? You know what? Let me split this video in two as well, so you can give that a try. So what you want to do is df dx and dg dx, and tell me what the results, aka derivative, of those are.